So here we have a table of the result of a certain test on students who were given a particular program, and the results of their post-test was collected from a 30 sample size, and it turned out that for program 1 there's only like 10 students who were able to have a better post-test, and 20 students their post-test was lower than their pre-test. For program number 2, 15 students were able to have a higher post-test, while 15 students also were not able to have a better post-test than their pre-test. And we just have a control group where there's like no program, and 5 students were able to have a higher post-test, and 25 students got a lower post-test. Now, remember when we were doing chi-square analysis, we needed to have like an expected value. All these things in front of us are like observed values. As you can see, we observe them to be like that, and the chi-square requires to have an observed and expected value. If you remember, the chi-square statistic requires us to have an observed minus expected squared all over expected, and sum to all of that. Alright, so what's in front of us is called a contingency table, and notice there's no available data for the expected, and hence we need to generate it ourselves. We need to generate the value of the expected ourselves. Alright, so how do we do that? Well, as you can see, we can actually get the number of students that took program 1, and the total number of students who took program 1 is 30, and also the number of students who took program 2 is 30. It doesn't need to be the same. It turns out that in this particular test they use the same number of sample size. So we see that for no program also 30, a sample size of 30 was used. Now we can also get the total of, we can try to get the total we can also get the total of students who passed, who has a higher score on the post-test, and in that case that's 10 plus 15 plus 5, that's 20, that's 30 students who passed the post-test, and 20 plus 15 plus 25, so that's 40 plus 20. 40 plus 20 is 60. So all in all, in this particular test, we used 90. So you can see the grand total from this side and that side is 90. So it actually means that if you would look at this part of the table here, the logic tells us that out of 90 test samples from each particular program and no program, 30 out of 90 had a higher post-test, and hence that is our expected percentage of students, and that's equal to a percentage of 1/3, or equal to 33%. And 60 out of 90 students did not have a higher post-test, lower post-test. So our expected percentage based on our analysis on the total is 60 over 90 is equal to 67%. Alright, so we would use this percentage to get the expected value of each of the particular programs. So let's say we wanted to get the expected value of program 1. We know there's a total of 30 students, and according to this, our expected result is 33%. So what is What is 33% of 30? Say 30 times 0.33. That's equivalent to 9.9. So we expect a 9.9 on program 1. How about how much do we expect for the students lower than the post test? Well, so let's try to multiply it. Let's see what we get. 0.67. We expect it to be 13.4. So I would repeat 20 times not 30, not 20. The total number is 30. It must be 0.67% of the total 20.1. Alright, that makes sense. 20.1. Now since for program 2 there's the same total number, so 33% of 30 we expect it to be 9.9, and 67% of 30 is 20.1. Those are expected, and it's also 30 in here, so we expect this to be 9.9, and we expect this also to be 20.1. Just to make sure we're clear that that's just to show that these are all our expected results based on the total ratio, and on the other side we have our observed results.